So in this lesson, we're going to be talking about solving exponential equations. So what we want to do is be able to solve exponential equations using properties of exponents and logarithms. And here's the standard that we're working on. Writing expressions, equivalent forms to solve problems, including those that use properties of exponents. Okay, so this is a review of something that we've learned previously. So this is when it's possible for you to rewrite the exponential expressions with like bases. So for example, in this one we have 5 to the n plus 10, But this one says 25, but it's possible to rewrite 5 as a power, to rewrite 25 as a power of 5. Therefore, we say that 5 to the n plus 10 is equal to 5 squared. So it stands to reason that the exponents must therefore be equal. So we end up with a simple equation. N plus 10 equals 2. Subtracting 10 from both sides, we get negative 8. Now it's okay to have a negative number in the exponent because that just means to reciprocate it. But we always want to double check to make sure it makes both sides the same. So negative 8 plus 10 gives us 5 to the power of 2, which is 25. So it's a valid solution. On the other hand, we have this one over here on the right. The bases are 9 and 27. 9 squared is going to give me 81. I see the square root of 27 is not 9, but I can write them both as the power of the same number. So I know that 9 is really 3 squared. Still being raised to the 8 plus 2. I'm just rewriting it in a different format. 27 is 3 cubed. And it also is still raised to the 4 times a minus 2. Using our exponential properties, I know that I need to multiply the power when I have power of a power. So this becomes 3 to the 2a plus 4. And on the right, we have 3 to the 12a minus 6. It's not really necessary to use that property because once I know I have the bases, I just know the exponents are the same. Yes, the exponents are going to be the same to get my equation. But I've already done the distribution, so now what's left is just rewrite my equation since the bases are both 3. So I'm going to subtract 2a from both sides, add 6 to both sides, and then divide by 10, giving me 1. So if I go back, I get 9 to the third power, which is 729. And then over here, if I put in a 1, I get 27 squared, which is also 729. Okay, now, that was a review of stuff we had learned before, but we know that must be a little bit harder if that was just a review. So what we have been learning about is inverses of exponentials. And so this is what we're going to need when the bases can't be written the same way. So when the bases aren't the same, cannot rewrite it so I have the same base on both sides. The first thing I'm going to do is I'm going to isolate the exponential expression. So that means on one side of the equal sign, the exponential expression term must be by itself. Then I'm going to do something that involves the inverse function of exponentiating, which is to take the log. So I'm going to go ahead and I'm going to take the log of both sides. And here's a little catch. Sometimes I may have to use my properties to expand the logarithm. And we'll see some examples of why we may have to do that. And then, just like we did with logarithmic equations, we then solve the resulting equation, checking for extraneous solutions. Okay, so let's go ahead and try this one. So I can't write 61 as a power of 2 because 2 to the 6th power is 64, but still not 61. So what I'm going to do is I'm going to take the log, and when I do take the log of both sides, whatever the base of my exponential function is, that is exactly what I want the base of my log to be. Okay, so now I'm taking the log of both sides and now I'm going to simplify. So over here on the right side, I see I'm taking the log of an exponential expression. So what we've learned previously is that when we have an exponent of the product in the logarithm, I'm going to go ahead and write that as a coefficient. So I have x times the log base 2 of 2 is equal to the log base 2 of 61. Now, what did I learn previously about taking the log of a number that's equal to the base of the log? Well, it's equal to 1. So this kind of cancels itself out because x times 1 is just x. So what I'm left with is x is equal to the log of 61 base 2, or log base 2 of 61. That is an exact answer. I could use my calculator and put this in and get a decimal expression, but this is the most precise answer, so I'm going to leave it exactly like that. Writing it like this is kind of the same thing as writing square root of 2 rather than rounding it to 1.4. This is more precise. Okay, so let's go ahead and do number 5. So first thing is I'm going to go ahead and I'm going to isolate the exponential. So I'm going to divide both sides by 4. So that's going to give me 7 to the power of n equals 37. So because it's not possible to write 37 as a power of 7, I know I'm going to have to use logarithms. So I'm going to take the log base 7 of the left, log base 7 of the right. So now I'm going to simplify this. So I'm going to take my exponent and make it a coefficient. Log base 7 of 7 equals log base 7 of 37. So remember, log base 7 of 7 is just 1. And so that tells me that n is the log base 7 of 37. I'm going to leave my answer just like that. Okay, now number 6. We may have to do the same way, but look at what happens when we get it. So when we isolate the variable here, I add 5 to both sides and I get 8, but it's possible to write 4 and 8 as a power of the same number. So I don't have to use logarithms on this one because 2 squared is the same as 4. And I add the multiply the exponents. So that's going to be equal to 2 to the 3rd power. So 2 times 3w equals 3. So I get 6w equals 3, or w equals a half. And then, of course, don't forget, go back and check your answer. Okay, so sometimes they get a little more complicated, but not too much more complicated. So let's look at number 10. So on number 10, I want to go ahead and I need to solve for the exponential, which is 5 to the p. So order of operations, -2 times 5 to the p plus 7. I need to get 7 away first. So I'm going to subtract 7 from both sides. So that gives me -70. Then I'm going to divide both sides by -2. And now I'm going to rewrite this as a logarithmic expression. So I'm going to take the log base 5 of both sides. And from previous problems, I know that this becomes coefficient, and log base 5 of 5 is just going to become 1. So I get P is log base 5 of 35. Now I could go a little bit further with this because 35 is the same as 7 times 5. So that would give me log base 5 of 5 plus log base 5 of 7, which this is 1. So it gives me 1 plus log base 5 of 7. Okay, last one, I promise. Let's do this one. So what would you do? So try pausing the video and see if you can come up with it yourself. Okay, let's see how it went. So we add 2 to both sides. Divide both sides by 6. And then I rewrite it as a logarithm. So log base 16, 16 to the 7y plus 2 equals log base 16 of 14. So I know that I'm going to end up with just this because this becomes a 1. I'm going to rewrite it over here. 7y plus 2 equals log base 16 of 14. So now I'm going to subtract 2 and divide by 7. So I get 7y equals log base 16 of 14 minus 2 all over 7. Be careful over here that when you're saying what you're taking the log of, it's very clear that it's the 14, not the minus 2. And that's all. Thank you.